Good morning, friends. I'm very happy to see you again. And today we are going to discuss another important aspect in the chemical bonding, which is called the polarity in covalent bond. See, when similar atoms are bonded by a covalent bond, you know what is a covalent bond? A covalent bond is a sharing of electrons. So this hydrogen is in need of one electron to complete its duplet, and this hydrogen is also in need of one electron to complete the duplet. So this donates one electron, and this hydrogen donates another electron, and these two electrons are common for both the hydrogen atoms. So similar atoms. These molecules are called homoatomic molecules. Similarly, you can look at the chlorine. Chlorine has 7 electrons in its outermost shell. So chlorine needs one more electron to complete its octet. So this chlorine has donated one electron, and this chlorine has also donated one electron. Both the electrons are common for this chlorine, and this is also a homoatomic molecule. In such cases, what will happen? You know what is electronegativity? Electronegativity is the capacity of an atom to attract the shared pair of electrons towards itself in a covalent compound. So, this is a covalent bond, and this hydrogen has a particular amount of electronegativity, and this hydrogen also has a particular amount of electronegativity. As this is a homoatomic molecule, both the atoms attract the shared pair of electrons towards itself with the same force or the same pulling power that is exerted by the atoms on the electrons. Therefore, what will happen? These electrons are neither moved towards this chlorine nor towards this chlorine. Hence, these electrons are at the middle. As they are lying at the middle, this chlorine does not possess any charge, and this chlorine also does not possess any charge. But if you think of the heteroatomic molecule, what is a heteroatomic molecule? Two atoms are different. The two atoms are different. So fluorine needs one electron for the bond formation, and the hydrogen also needs one electron for the bond formation. Similarly, in the next molecule, chlorine needs one electron for the completion of the octet, and the hydrogen needs one electron for the completion of the duplet. So they keep the two electrons in common. The HF molecule and the HCl molecule, these molecules are called heteroatomic molecule. Different atomic molecule or dissimilar atoms are present. So now what happens when you compare the electronegativity of a fluorine and hydrogen? Fluorine is found to be more electronegative than hydrogen, and the chlorine is found to be more electronegative than hydrogen. So in such situations, what happens? The shared pair of electrons are attracted more towards fluorine, and here in this molecule, they are attracted more towards chlorine. Therefore, they are not at the center, they are shifted. The electron density is found more around the fluorine, and it is found more around the chlorine. And because of this shifting of electron density, the fluorine possesses a partial negative charge, and the chlorine possesses another partial negative charge, and the hydrogen possesses a partial positive charge in this molecule and in this molecule. Therefore, what happens? The entire molecule becomes a polar molecule. Polar means two polarities in a molecule. So, polar molecules. And these polar molecules are also called electrical dipoles. Electrical dipoles. And these polar molecules, what will happen to them? They will orient themselves in an electric field. Suppose you are having two electrical plates and you are passing electricity, and these molecules are kept in between. Means what will happen? The negative side of the molecule will try to turn towards the positively charged plate, and the positive part of the molecule will turn towards the negative part, negative plate. So what will happen? They will get orientation. They will change their orientation. And because of this change in the orientation, the intensity of the charge on the electrical plate will diminish. Once the orientations, all the molecules get oriented towards the oppositely charged electrical plates. They will align in such a way that the charges are oriented towards the oppositely charged plates. And because of this, what will happen? The intensity of the charge on each plate will get diminished. So this is what is polarity in the covalent bond. Now the covalent character in the ionic bond. So look here, we have seen how the polarity is induced in a covalent bond. Now we are going to see how the covalent character is found in the ionic bond. That is why these bonds are called intermediate. So they are normally the bonds are neither covalent nor ionic. They are somewhere in between these two characteristics. And this intermediate bond between the covalent and the ionic is called the polarization of ions. What is this polarization of ions? When oppositely charged ions approach each other, what happens? See, the positively charged cation is spherically symmetrical, and the negatively charged anion is also spherically symmetrical. Actually, this symmetry is assumed when these ions are independent. They are not under the influence of the other ion. But when oppositely charged ions approach each other, what happens? The positively charged cation is having an attraction towards the electron. Originally, it has lost the electron to attain the stability. But now, as it is positively charged, it is its electrical nature to attract the excess electronic cloud. And because of that, what will happen? The cation will try to distort, or it will try to deform, or it will try to polarize the electronic cloud in the anion. And because of this polarization, what will happen? The anion will lose its spherical symmetry, and the electronic cloud will be distorted or deformed or polarized towards the cation. This is called polarization. So what is polarization? It is the distortion or deformation of the electronic cloud of an anion by a cation. Now you can see the polarization of the cation is much less when anion is compared, because the cation, it is already electron deficient. So the electronic cloud that is present in the cation cannot be oriented or cannot be distorted. But anion, it is bigger in size. Whenever you compare the sizes of a cation and the anion is found to be bigger because of the excess electron. Cation is found to be smaller because of the deficiency in electron. So because of this big size, polarization is more pronounced in the anion than in cation. So the polarization of ions results in a high electron charge concentration between the two nuclei, and this results in the formation of a covalent bond with a high degree of polarization. So the polar nature in a covalent bond. So this high degree of polarization or the distortion in the electronic cloud, it makes the covalent bond much stronger than, that is a polar covalent bond is more stronger. It is stronger than covalent bond or ionic bond. So the compound which is purely ionic or the compound which is purely covalent, is found to be of less strength than a polar covalent bond, which is a mix-up of the ionic and the covalent bond. And also the extent of the polarization, how far the polarization is effective. The extent of a polarization depends upon the polarizing power of the cation and the polarizability of the anion. Polarizing power and the polarizability of the anion. Actually, the polarizing power and the polarizability, and these two things are discussed by Fajans, which is called the Fajans rule. I will read out these rules one by one, and then I will explain with the previous slide. See, the cations with a smaller size have high polarizing power. That is, they cause a polarization of electronic charge cloud of an anion to a greater extent. And the second point is the anions with a large size have high polarizability. That is, their electron charge cloud can be deformed easily. And the third point, for effective polarization, there should be a high charge on the cation or the anion or both. And the fourth point, the cations with a pseudo inert gas configuration. Look here, this is a very important point. Or with inert pair configuration. See, the pseudo inert gas configuration is highly unstable. And also, inert pair configuration is highly electron withdrawing. So they have a high polarizing power, while cations with the inert gas configuration, see, when the cation attains inert gas configuration, naturally it will not have any attraction towards the electronic cloud. But a pseudo inert gas electronic configuration will have attraction towards the electronic cloud. And also inert pair configuration will have attraction towards the electronic cloud. But that atom with the inert gas electronic configuration will not have the attraction towards the electronic cloud, and hence it will have the low polarizing power. So these are all the four important ideas given by the Fajans. So this is called the Fajans rule. So the summary of the Fajans rule is presented here. The cations, when they are small in size, when they are high charge, actually altogether this can be stated as the charge density. Small size with a high charge. This is called the charge density. We have already discussed what is charge density in previous classes. And also, when the size is small and the charge is high, they have high polarizing power. And also, when you compare the polarizing power, the pseudo inert gas configuration will have more polarizing power with when you compare the large size and a small charge. Actually, this should be small charge, large size and small charge, and this inert gas configuration. So these are all the comparative study. And when you compare the anions, large size and high charge will have high polarizability when you compare small size and a small charge. Actually, here it is size is wrongly written. It has to be small charge. So this is the summary of the Fajon's rules. Now you can see effects of effects of the polarizing. Just a minute. Effects of the polarization. Look here, bromides and iodides. You can see, you can think of the fluorides, you can think of the chlorides. Fluoride has a high charge density. Suppose if you take a sodium fluoride, sodium is a small, fluorine is also small. So sodium has a high charge density, fluorine also has a high charge density. So naturally we will expect that Sodium fluoride will be highly stable because the sodium is ready to donate one electron and the fluorine is ready to accept one electron. And also fluorine is found to be more electronegative. The highest electronegativity is of the chlorine, is of the fluorine. So it is naturally we are expecting that the sodium fluoride has to be highly stable. But when you compare sodium fluoride, sodium chloride, sodium bromide, sodium iodide, bromides and iodides are found to be highly stable because of the high lattice energy. And this lattice energy was found to be much more than the calculated. So the crystal is found to be extra stable. And this extra stability is due to the polar covalent bond because bromine and iodine, they are bigger anions. Bromides and iodides are bigger anions. Therefore, they can be easily polarized. And because of the polarization, the high lattice energy, they attain high stability. And the second point, when polarization increases, solubility in a polar solvent decreases. This is also practically observed. So, potassium iodide, potassium bromide, potassium chloride, potassium fluoride, if you compare the solubility of these substances in polar solvents, when polarization increases, solubility in polar solvent decreases. And the third point, normally ionic compounds are very hard. That is what we have seen in the characteristics of ionic compounds. Ionic compounds are found to be very hard. But the hardness of the ionic compound, it is decreasing when the degree of polarization increases. So polarization increases means automatically the hardness of the ionic compound decreases. And the next important point is the percentage of ionic character of a polar covalent bond. The percentage of ionic character, each covalent bond has a certain amount of ionic character. So the percentage of ionic character depends upon two important factors. One is electronegativity difference and the other one is dipole moment of the compound. What is this electronegativity difference? Look here, electronegativity difference, if at all electronegativity difference is not there, then the bond is purely covalent. The electrons are at the center. If electronegativity of A is higher than B, then the electron density is found more around A. So what happens? A becomes delta negative, B becomes delta positive. If the electronegativity of B is higher than that of A, then the electron cloud is more found around the B. So A becomes delta positive and B becomes delta negative. And because of the difference, if the difference is more, then the shifting of the electron cloud will also be more. If the difference is less, then the shifting of the electron cloud will also be less. If the difference is nil, there is no shifting at all. The electrons are found at the center. So, having this idea in mind, Pauling and Hannay Smith, and these two people, these three people actually, they proposed some empirical formulae. And the Pauling's empirical formula is the percentage of ionic character is equal to 1 minus e power minus 1 by 4 chi A minus chi B, where chi A and chi B are the electronegativities of A and B respectively. And also Hannay and Smith formula, the percentage of ionic character is equal to 16 chi A minus chi B plus 3.5 chi A minus chi B whole square. But both give only approximate value. See, this is the drawback of these equations. They give only approximate value. See, when you think of the dipole moment, what is dipole moment? A dipole will experience a moment in a non-uniform electric field. When a dipole molecule is kept in a non-uniform electric field, it will try to orient itself in such a manner that it will have less energy. So, how the molecule is getting oriented and what is the moment that is shown by the molecule in a non-uniform electric field? It is called a dipole moment. The purely covalent compound shows zero dipole moment, completely ionic but attached together. That shows very high dipole moment because dipole moment itself is the charge multiplied by the distance of separation. So the distance of separation of the charge is as maximum as the bond length or the internuclear distance in the case of ionic compound. That is why the dipole moment is found to be very high. But a dipole moment is found to be zero in the case of covalent compound. Now, when you think of the charge separation, in covalent compound, the charge separation is zero. But in ionic compound, the charge separation is equal to the internuclear distance. So when you compare the actual dipole moment observed and the dipole moment if the compound were a pure ionic compound, it is that will give you the percentage of the ionic character. So the percentage of ionic character is equal to actual dipole moment divided by dipole moment of the pure ionic compound multiplied by 100. So if you take a hydrogen fluoride, the HF bond length or the internuclear distance is a 0.92 angstrom unit. So using the 0.92 angstrom unit and the +1 charge here and the -1 charge here, it is calculated that the dipole moment of a pure ionic compound will come around 4.42 d by. The d is the unit of dipole moment, which is d by. And when you measure the dipole moment experimentally, you are getting around 1.98 d by. So if the hydrogen fluoride molecule were purely ionic, the dipole moment will be 4.42 d. If it is a purely covalent, it will be 0. Now it is 1.98, somewhere in between. So the bond between hydrogen and the fluoride possesses 45% of ionic character and 55% of covalent character. So this is how the percentage of ionic character is calculated using the dipole moment values. And now the why this dipole moment value calculated or the percentage of ionic compound, a percentage of ionic character calculated is approximate, because the ionic contribution is only part, and also there is a lot of differences in the sizes of the cations and anions, and also the hybridization involved and the lone pairs present in the atoms will also affect the ionic nature of the covalent compound. And the next one is the relation between dipole moment and the structure. Normally, the spatial arrangement of atoms plays an important role in the dipole moment of the molecule. Look here, the dipole moment of a molecule is the vector sum of the dipole moment of various bonds. Obviously, the polar or non-polar nature of a molecule will depend upon the arrangement of atoms in the molecule, which means that the bonds may be polar and yet the molecule may be non-polar. The bond may be polar, yet the molecule may be non-polar. Look here. This is carbon dioxide molecule. The net dipole moment is the vectorial sum. What is a vector? Vector is the line segment drawn in space which would represent the magnitude and the direction of any physical entity. So this carbon, so this, if you take this carbon and oxygen bond, actually this bond is polar because oxygen is found to be more electronegative than carbon. So this is the direction of the bond moment. And this carbon and oxygen, this is the direction of the bond moment. But because they are equal in magnitude and opposite in direction, they will cancel out each other. And hence the dipole moment of the carbon dioxide molecule becomes zero. If you take water molecule is bent shaped because of the lone pair present here. Lone pair bond pair interaction makes the water molecule bent. Now, oxygen is found to be more electronegative than hydrogen. So there is a bond moment in this direction and another bond moment in this direction. So the vectorial sum, when you add these two, the vectorial sum, the resultant vector, we are getting in this direction. And because of this, the molecule has the permanent dipole moment 1.84 d by. At the same time, if you take a boron, BH3, the hydrogen is more electronegative. So this is a vector, this is a vector, this is a vector. So the molecule is triangular planar. So all these vectors will pull in all these three directions and the net pull will be zero. That is why BH3 molecule is with a zero dipole moment. But if you look at ammonia, ammonia is not planar. Ammonia is pyramidal in shape. This pyramidal shape is because of the lone pair present on the nitrogen. Because of lone pair bond pair interaction, it is bent, so it assumes the pyramidal shape. Now, nitrogen is found to be more electronegative than hydrogen. So here is a vector, and here is a vector, and here is a vector, and the sum up of all these vectors will result in the resultant vector having the dipole moment 1.49 d by. If you take a carbon tetrachloride or methane, methane is a tetrahedral in shape and the electronegativity of a carbon is higher than hydrogen. So the four vectors are oriented in four directions. If you take a carbon tetrachloride, it is also tetrahedral in shape, but the only thing is the vectorial direction is changed because the chlorine is more electronegative than carbon. Both methane and the carbon tetrachloride, the dipole moments are zero because of the symmetry. But at the same time, if you take a methyl chloride, see, one vector is downwards, the three vectors are upwards, and also these vectors are different in their magnitudes. So methyl chloride has net dipole moment, whereas a carbon tetrachloride or methane, they do not have net dipole moment or they show zero dipole moment. It's all because of the spatial arrangement. But all these compounds are having polar bonds. Their bonds are polar, but as a whole, the molecule is non-polar because of the symmetry or because of the spatial orientation. So the dipole moment and the structure. Knowing the dipole moment, you can come to a conclusion what may be the structure of the molecule, or because of the structure, what would be the dipole moment of the molecule. So the dipole moment and the structures, they are all interrelated. Later on, we are going to see the applications of the dipole moment measurement and how a structure can be confirmed using the dipole moment studies. That is our next discussion. And this is dipole moment actually, the magnitude of the charge multiplied by the distance. If we take a hydrochloric acid, the magnitude of the charge is 1.602 into 10 power minus 19 coulomb, and the bond length or the internuclear distance is 1.275 into 10 power minus 10 meter. It has to be substituted in SI units. So this, this becomes a meter coulomb. Actually, 1 d by is equal to 3.338 into 10 power minus 30 meter coulomb. So mu can be arrived in units of d by, you are getting 6.12 d by. But the actual value of the dipole moment of HCl is 1.03 dBi. So it is concluded that HCl molecule is mostly covalent and the charge is not separated to the bond length. There is only a partial separation of the charges. And because of this partial separation only, the percentage of ionic character becomes very less. Now, when you think of the multi-atomic molecules, whether it is a polar or non-polar, that depends upon the arrangement of atoms, the bond length, and the bond angle. As we have discussed earlier, carbon dioxide molecule or carbon sulfide molecule, a carbon disulfide molecule, they are non-polar. But water is a polar because of the lone pair and the bent structure. Similarly, sulfur dioxide is a polar because of the bent structure. Ammonia is a polar because of the pyramidal structure, whereas a carbon tetrachloride or methane is non-polar because of the tetrahedral symmetry, but methyl chloride has polarity. And another important bond we are going to discuss is a hydrogen bond. Look here, when hydrogen is attached to a highly electronegative atom like fluorine, oxygen, and nitrogen, then what will happen? A polarity is induced. And because of this polarity, the dipole molecules will get associated and there will be a weak bond between the negative part of a molecule and the positive part of another molecule. That is, the attractive force which binds hydrogen from one molecule with the electronegative atom such as fluorine, oxygen, and nitrogen of another molecule of the same substance is known as hydrogen bond. So the hydrogen atom, it is a bridging between two fluorine atoms of the molecule. Look here, if this is a fluorine, this is another fluorine. One side it is covalently bonded, and the other side it is hydrogen bonded. Therefore, this hydrogen is functioning as a bridge between two fluorine atoms. And because of this, what happens? HF, HCl, HBr, HI. HCl, HBr, HI, they have the less tendency to form hydrogen bond, whereas HF has more tendency to form hydrogen bond. And because of this, KHF2, this is a complex molecule, that is K plus HF2 minus. This is the structure of the coordination sphere. Only KHF2 is existing, whereas KHCl2 or KHBr2 or KHI2, they are not possible or they are not existing because of the hydrogen bond. And look here, water molecules, they form hydrogen bonds. And because of the hydrogen bonds alone, water is existing in the liquid state. Similarly, alcohols form hydrogen bond and the carboxylic acids also form hydrogen bond. Look here, this is a type of hydrogen bond where only two molecules are linked. This is called a dimer. Dimer. And the strength of the hydrogen bond is between 3 to 10 kilocalorie per mole. That means that it is very weak bond, but covalent bond strength is more than 100 kilocalorie per mole. So you cannot easily break a covalent bond, but you can very easily break a hydrogen bond. Mere heating is sufficient. And I want to give you one extra information. Originally the molecular weight of the acetic acid was determined by the freezing point depression method, which is called the Rast method, or a colligative a method which is based upon the colligative property, a cryoscopic method. When they calculated the molecular weight, they got double the molecular weight. But originally the acetic acid is 63, it is 120 means. Then people found out that the acetic acid molecules are associated, and the two molecules associate and they will exist as one single particle. And they thought that it is because of a weak bond which holds the two acetic acid molecules together. And later on, it was confirmed to be the hydrogen bond. This is how the hydrogen bond was found out. And I think the 40 minutes is over. Yes.